set of comments. Now, the logistic regression in the GLM in general, has a very important advantage. It always gives you a smooth, continuous, predicted probability of class membership, and it is very easily explained. So you have a nice mathematical equation that you can, in most cases, decompose into some main effects and perhaps some interactions. And if someone's asking you what the model is doing, it's very easy to communicate that. So that's one of the very big advantages that we have to point out at all times. And it does capture effectively global features of data because it essentially leverages information from all across the board. Now, when we enter into data mining domain, there are lots of different techniques, a lot of different algorithms available out there with the emphasis on different parts. So what I will do here, I'll run a quick exposition of CART just to highlight the differences. In fact, for a long time, CART was one of the key competitors with the logistic regression. To the point that some people even thought possible ways of recasting CART as a part of a logistic regression. Now, what I'm about to show here is that basically to claim that trying to represent CART as some kind of GLM solution is a pointless exercise because they operate under very different assumptions and very different philosophies. And instead of trying to find similarities where there are none, you might as well use it, keeping that alternative philosophy in mind. CART trees were, of course, introduced by Bryman, Friedman, Olshan, and Stone back in 1984. So it's not an ancient methodology, but it's a pretty well established compared with everything else that we have. And the original claims, they're valid to this day, is that it automatically separates relevant predictors from irrelevant. Doesn't require any type of variable transformations. It purposes to outliers, yields relatively simple and easy to comprehend models, and so on. And now the approach is fully described in the CART book. We have training classes, we have everything. But in general, at the top level, what we are doing here is a process of binary recursive partitioning. Now, here's the formal definition of what it does, and you probably, after all, it's the Salford conference, so the great, almost all of you kind of understand what's going on. But think about it from the philosophical point of view. What is it that you do in CART? You start with a data set that could have millions of records. And at the very beginning, you're fitting kind of a Y bar, or overall response rate to everyone. Now, but what you're doing at the very first part of that process is that you start looking for all possible ways to slice your data set into two mutually exclusive regions. And you do it in a somewhat restricted way by allowing only one variable at a time, one split point at a time. But as you're doing it, you are essentially slicing the observational part of the data set. And by the time you've completed that initial split, whatever happens on one side evolves independently from what will happen on the other side. And that's a major shift in the paradigm because from the very beginning of the process, you already partitioned the universe into two separate universes. And they are no longer capable of influencing each other. And that partitioning keeps on getting bigger, bigger, and bigger because as the splitting process continues, you are dividing all of these subsets, separating them from each other, and within each subset, an independent flat surface is being fit. So essentially, if you ignore the fact that we need to have the target variable and everything, what you're doing in CART is some kind of intelligent clustering of the universe into mutually exclusive pieces. If you think back to GLM or logistic regression, that approach operates on a very different set of assumptions. In a logistic regression, you never partition your space. what you're doing, you're throwing in extra dimensions into your modeling solution, like in the forward stepwise. So again, you start with, say, a flat surface that fits them all, but then you're trying to add variables one at a time, still covering the entire space. So you're working in the variable dimension. And that's the general characteristic of all classical techniques. The data set remains intact. You're just adding dimensions, and hopefully you'll exploit correlations and partial correlations with the response variable. Not in CART. In CART, instead of adding dimensions, you're slicing data into smaller and smaller pieces. And that alone would render any attempt to convert CART model into an equal representation as a logistic regression is bound to fail, because the underlying philosophy has changed dramatically. CART is an example of an algorithm that learns strictly from the data itself. There are no assumptions, no particular transformations that an analyst would introduce. Everything happens on its own by following the data path. And in a sense, CART is just the starting point. You will find that all of the subsequent algorithms are kind of built up on top of CART using fancier search techniques or more convoluted modeling structures. Like, for example, Mars is essentially a CART process recast into some kind of splines framework, where instead of fitting constant pieces of planes in different mutually exclusive parts of the space, you'll start fitting slopes on an overlapping partition, and you also require the elimination of points of discontinuity. I mean, we sometimes call Mars as a CART in disguise. And if you work with Mars, you may not even know that underneath there is a very deeply hidden CART algorithm or something that operates under the same set of rules. And of course, when you go into TreeNet and random forest, things kind of get more complex, but you're essentially saying one tree is great, but not enough. So there is still room for improvement if we produce multiple trees and combine them together. And the only difference between TreeNet and RF is that in RF, you combine independently grown trees, so you operate under the concept of bagging, whereas in TreeNet, you combine the sets of dependent trees. It's a sequential process where each subsequent iteration attempts to improve performance gained in the previous set of iterations. So, and there's all kinds of fine differences that I'm not going to talk about at this point. Okay, so that's the essence of CART process. So now let's compare these two and see where they differ and where we could possibly exploit very useful connections. Just at the top level, in the CART, we have automatic analysis, effective missing value handling, interaction detection, and the data-driven learning. Now, I don't have much time to elaborate on some of these points, but if you think about missing value handling, CART has that concept of surrogate splits. In other words, when you're searching for a partitioning of the space right now, in addition to that optimal split point, you're also looking for alternative partitions on different variables that could replicate more or less the job of the original partition. We call it a surrogate split. Or one simple way to think about it is if you're splitting a given set of, there's the given population, and the primary splitter happens to be income. So you know all the low-income folks go on one side, all the high-income folks go on the other side, but then there is also that part where the income, for whatever reason, is undefined because they refused to supply it. Now, the problem with treating that separate group as on its own is that it effectively mixes both tails of the original income distribution. Some people did not report income because it's low, some did not report because it's too high, and when you mix all of them together, you can't really pull them all on one side or another side without committing a gross error.